Yeah.
It's really cool to think you're making the moon in a lab, basically.
Yeah, it's very cool.
You're listening to The Cosmic Cast.
Hello, and welcome back to another episode of The Cosmic Cast. I'm John Panny-Fisher, and I'm with the regular co-hosts of Tom Harvey and Ricky Bahir.
Hello.
And this week, all the way from the Netherlands, is Josh Snape. How's it going?
I feel like all the way from the Netherlands is misleading.
Well, you're sat in the Netherlands right now.
I am definitely not Dutch, but yeah, I'm an imposter. Yeah, I'm good.
Excellent. So we were just chatting a bit before we started recording then. So you're still able to do a little bit of lab stuff. And so you're in the Netherlands. How long have you been there for now?
So this is just coming up on 2 years now.
Okay.
So it's part of a Marie Curie fellowship.
Mm-hmm.
So yeah, when the pandemic sort of started and it became clear that things were going to get interesting and the lockdown was going to sort of become more serious in the Netherlands, it was decided that certain people could go into the lab. So as long as there's kind of just one person in a lab at a time, then it's fine.
Yeah.
And so yeah, it's been in some ways quite therapeutic, I think, because the lab work that I'm doing, it's all sort of experimental petrology stuff. So there's just lots of like manual, just kind of tinkering around. So yeah, I can do the sort of all the boring spreadsheets and like writing up of stuff at home in my apartment. But yeah, if I really need a break, I can just kind of go and like lave some little graphite capsules for the piston cylinder press. So it's quite like, in that sense, it's quite like I don't know, it's almost Zen-like sometimes. You just like do this, and it's very different to data processing that I'm used to from sample analysis. So.
Yeah, it's quite mindful, isn't it? I think that's that kind of lab work for sure.
Yeah, and it's good. I mean, you can also just catch up on like podcasts like this. So yeah, it's quite nice. It's often just spend my time listening to Radio 4 or Adam Buxton or something. So yeah.
And if any of you, of course, in the audience are listening to this while doing some lab work, don't forget to like, comment, and subscribe.
Great plug.
Very good.
You're probably the one person that would apply to it is actually on the podcast. So.
No, but it's true though. Yeah, I love listening to like podcasts and stuff while I'm running the mass specs and stuff.
It's quite good. Like a certain sort of mindless kind of activity to be doing.
Yeah.
Like there's a threshold where if it gets like, I don't know, definitely like reading is out of the question. I can't focus on any sort of reading. But like some like really mindless data processing is it's like perfect podcast fodder. So just kind of line them up.
Yeah, absolutely. Yeah, I really enjoy that kind of thing. Yeah, I'm really looking forward to when we get back into the labs. That'll be nice to be able to break up the day a bit and be able to leave this town, which would be quite nice.
Yeah, Amsterdam is definitely an interesting place to be stuck for lockdown. So yeah, it still seems quite busy as far as I can tell, but I don't know. It depends who you talk to. Some people swear that the lockdown has been very effective. I don't know. I'm not so convinced. Just looking out of my window.
But anyway, so before you were in Amsterdam, but you were also in Sweden for a bit as well. So you're quite a well-traveled person, really.
Yeah, I was super lucky. That was kind of the start of, I guess, what we were going to sort of talk about later in terms of all the lead isotope work that I do.
You're a lunar petrologist predominantly, I guess. Mention.
So I mean, I can just start from the beginning if you want. So I did my undergrad at UCL down in London, and when it got towards I did one of these these MSci 4-year undergrad courses that they do.
Yeah.
And so yeah, I needed to choose a 4th-year project, and I didn't know what to do, but I knew that I was really enjoying a lot of the planetary science courses that I've been doing. And I sort of stumbled into what was then the regional planetary imaging facility at UCL, which I think doesn't exist anymore. And yeah, Katie Joy was there, and she was like, I've got this lunar meteorite. It would make a really good MSci project. So yeah, she is the one who is responsible for all of this, basically. And yeah, that led to a PhD with Katie and with Ian Crawford. So continuing a bit of work on some lunar meteorite samples, but then also looking at Apollo 12 soil samples. And that was all fairly basic kind of geochemistry and petrology. And then, yeah, in 2014, there was a very brief stop off in the Open University, but then in 2014, I went to Stockholm and basically got thrown in at a deep end with uranium, lead, and lead isotopes. So, yeah, and then I got this fellowship to come to Amsterdam, and that's been again a sort of a change in subjects. As I say, sort of more experimental petrology and sample analysis.
How have you found that transition going from isotope geochemistry to experimental petrology?
Yeah, I guess it's always a bit nerve-wracking when you're changing subjects. So, but I think I found the transition this time around, like coming to the Netherlands and to the VU in Amsterdam, I found that less nerve-wracking and intimidating than when I first went to Stockholm. I think there's a sense in which you kind of, initially when you're asked to sort of transition into something a bit different, it's terrifying, and you have all the imposter syndrome stuff of worrying about whether you're really good enough and whether you can adapt quick enough. But then I think once you've done it a few times, there's certain things somewhere at the back of your head that reassures you that you'll be able to manage, and you just get on with it day to day, and it normally works out. You normally make some stupid mistakes to begin with. I definitely, like, when the first kind of compositions I was making from my first experiments, I definitely made some mistakes. But my boss, Wim, was very patient and guided me through like I was a sort of fresh undergraduate all over again. So it was good.
That's awesome.
You're on a Marie Curie fellowship there.
Yeah.
So you must have been buzzing when you got that, because it's not an easy thing to get.
Yeah, it was really nice. It was actually, it was nice in many ways. So on a personal level, it was good because my girlfriend is also doing a PhD in Amsterdam.
Oh, wow.
And so we had been like doing the whole long distance thing, which I guess many academics are familiar with, just because of the nature of the work. So yeah, on a personal level, it was great because we'd been doing a year of flying between Amsterdam and Stockholm. So now we're able to be together in Amsterdam, which is obviously very nice. It was also nice just because the project is something that I think we're quite like enthusiastic about, like myself and my sort of both my former bosses in Stockholm and also Wim here in Amsterdam. I think we're all quite excited about what we can do with it, because it feels like a little bit different, to a bit of a different approach to some of these questions about the early evolution of the moon.
I guess that leads us a bit into what exactly you have been doing with some of these experiments then. So you've been trying to understand the crystallization of the lunar magma ocean, is that right?
Yes. And anyone listening to this who's familiar with like lunar magma ocean crystallization will maybe think that doesn't sound so original in itself. But I guess as a way of an introduction, we have this concept, which I guess most of your listeners maybe have heard of the magma ocean.
We've touched on it before, yeah.
Yeah, and so it's basically a mechanism by which we can explain the different lithologies that we have in the sort of lunar sample collection. And in a very simplistic sense, you end up with a north-acidic rich sort of flotation crust, which makes all the kind of white highland material that we see on the moon. And you end up with all the mafic, all the iron and magnesium rich source materials for the dark Mare basalts that we see on the near side of the moon. And so it provides this mechanism for that. So I guess to explain why what we're doing in Amsterdam now is a bit different, I need to kind of go back to Stockholm and some of the work that we were doing there. We were using SIMS in the Natural History Museum in Stockholm to measure lead isotopes in lunar samples. So people are, or for a long time, people have used uranium and lead as a way of dating all sorts of geologic materials. And generally that relies on finding something that will work very well as a sort of geochronometer, like because it will incorporate lots of uranium into its crystal structure.
I guess for the listeners, that's based on the principle that uranium decays into lead.
Exactly.
If you know the rate of that decay, then it acts as a chronometer.
So exactly. So essentially, if you think that your crystal that you're measuring should not have incorporated any lead in when it first formed, and it should only have incorporated uranium, then any lead you measure is stuff that is the result of decay. And because we know the rate of that decay, we can work out how old things are. What we were doing in Stockholm, though, got a bit more different, a bit different to that, in that we started focusing on other mineral phases in lots of lunar basalts, including things which should be effectively the inverse of zircon. They should only incorporate lead as opposed to uranium. What that does is that gives you a way of getting your kind of isotopic sort of fingerprint, this sort of almost sort of genetic identity of the source material that the basalts have come from. So it was very successful, and it gave us a way to both get very precise ages of the basalts, work out when they were placed onto the lunar surface, but it also gave us these compositions, which, like I say, they're like a fingerprint of what material the basalts are from, and they tell us about what the composition of the sort of the sources in the lunar mantle would have been. And that combination of both a timestamp and also a composition means that you can start playing games in terms of modeling the evolution of lead isotopes in the moon. The problem that we have, though, is it's all of our models for how lead isotopes evolve, they rely on assumptions to do with the partitioning behavior of uranium and lead. So any mineral that crystallizes will incorporate different proportions of elements depending on the nature of its crystal structure. And this is what we refer to when we talk about partitioning behavior. And for things like uranium and lead, but also for some of the other radiogenic isotope systems that we look at, so rubidium and strontium, or samarium and neodymium, some of those partitioning sort of behaviors are not very well constrained. And so the idea that we wanted to sort of experiment with here in Amsterdam was essentially to re-simulate sort of phases of lunar magma ocean crystallization and see where uranium and lead is going at different points, and essentially see if we can make our models that come purely from analytical data kind of connect up with our experimental data. So yeah, what we do in the lab in Amsterdam, it's no different to what other experimental petrologists are doing, but we essentially have high purity oxide powders or carbonate powders, and we mix them up to simulate a particular starting composition that we want. So for example, I say, oh, I want to look at something that simulates what we think sort of 75% of magma ocean crystallization on the moon would look like. And so I just mix up a certain amount of iron oxide and magnesium oxide and calcium carbonate. You sort of grind them up in a pestle and mortar, make sure everything is homogeneous. You have to go through this process of decarbonation for any of the sort of carbonates that you add in there. It's just a question of heating it up to a certain temperature. And then we melt that composition into, we melt it and we quench it into a hopefully homogeneous glass. And then that has to be ground down again. And essentially we just put tiny quantities of this dust that we make, this starting dust, into little graphite capsules. People will use different capsules for different sorts of experiments. Graphite is quite good because it effectively generates sort of a nice low relatively reducing conditions
to simulate the moon, basically.
Yeah, as much as we can. And then that all goes, the sort of little graphite capsule then goes into a little platinum capsule, and there's like layers of complexity there. But essentially what you're doing is you're just putting this inside a little graphite furnace, a sort of external graphite furnace that sort of conducts the heat and heats up the sample whilst you're simultaneously squeezing it in the high pressure press. So a lot of the experiments I do, they are, say, around 1200 degrees Celsius and maybe 1 gigapascal. And you leave that running depending on what temperature and pressure you're doing. You leave that running for a certain number of hours or sometimes even days, and then quench it. And at the end, you end up with a slightly squeezed little capsule that you then just mount up like you would with any other rock sample, and you polish it and just analyze it.
So
it's,
cool.
It's really nice.
Yeah.
It's really cool to think you're making the moon in a lab, basically.
Yeah, it's very cool. It's sometimes hard to get across to people as well. It's also it's another one of these things, a bit like with the laser ablation stuff, with the sort of shooting lasers at moon rocks. It sounds a lot cooler than it is. The fact is that yes, I'm doing things at high pressure, but I'm doing things at high pressure over a very small volume. So it's like it's these capsules. My sort of actual sample that I analyze at the end of all of this is maybe sort of 3 millimeters long and 0.5 millimeter across or something. So they're very small and they don't look particularly impressive. Some of them look quite pretty. You get some really nice crystals forming if you get it just right. You get some nice grains forming. I've got some really nice sort of skeletal olivine crystals. Yeah, some really cool textures.
So how do you identify, I mean, is it specific conditions for different phases of the magma ocean that you're looking at?
Yeah, and this is going to be, I mean, the obvious sort of question of what follow-on experiments you would like to do. This is probably where this starts to become interesting. For the time being, I've just done a fairly limited range of kind of temperatures and pressures, primarily for the sake of just making sure that I crystallize all of the kind of important mineral phases that we think would be in the magma ocean. So, I mean, ideally, what you would love to do is to simulate every single step and crystallize every single phase. The problem that you have is when you start getting to tiny little accessory phases, sometimes even ones that are not that tiny. So things like ilmenite, iron titanium oxides, which presumably are quite important in terms of, for example, we know that there's a huge difference in titanium content between basalts that were collected at Apollo 11 and Apollo 17 versus basalts that were collected at Apollo 12 and Apollo 15. And we also see a difference in terms of the lead isotopes. So it will be good to know, for example, well, can we explain that difference in terms of the partitioning behavior of uranium and lead in things like ilmenite and spinel? The problem that we have with those accessory phases is that if you just kind of crystallize your your expected lunar magma ocean crystallization sort of compositions, you get very, very small ilmenite crystals forming. You get these piddly little sort of laves of ilmenite. And I need a certain size of crystal in order to do my laser ablation analyses and measure the trace elements. So the workaround for this is you basically start fiddling your compositions a little bit, where you just kind of jack up the titanium and the iron content and force it to crystallize loads of ilmenite. So I guess that's a very long-winded way of answering the question, but the point is that we focused on a few parameters essentially to create a sort of a fairly complete suite of minerals that we would expect in the LMO. So at the moment, we've not explicitly gone through every stage of some of the previous models that have been completed. But that would be something we could do in future.
It's really cool that you have that control, though, over what minerals you can crystallize and stuff like that.
Yeah, it works better for some things than others, I've discovered. And we're not the first people to do this, certainly. I've been doing the laser ablation work in Munster. And when I was last there, I was complaining about the size of my ilmenite crystals, amongst other things. And Stefan Clem, who is far more experienced as an experimental petrologist than me, he was the one who was advising that we sort of take some of these approaches. And I mean, he's right. It works beautifully. He's got some great studies from sort of 2006, I think, where they did lots of work partitioning
I know that paper.
and also some on phosphates as well. And it's a really neat trick. I got curious about potassium feldspar, and I've tried the same trick with that. That's much harder. I can't seem to make any decent sized K feldspar grains, but you know, we're getting to the really nitpicky side of things now. In terms of the kind of major silicate phases.
Yeah.
For the LMO, I think I'm fairly well covered, and now it's just a question of the good old fun task of like trawling through the data and writing it all up.
So why is it so important to understand lead evolution? What's that telling you relative to other chemical systematics?
So it's essentially just another tool in our sort of toolkit for trying to decipher some of the big questions about the evolution of the moon. So what we were really keen to do when we first started measuring sort of lead isotopes in Stockholm in the way that we are doing, we wanted essentially to try and define the age of the moon. Is the kind of really simplistic answer.
I guess that's it's a bit. The age of the moon is fairly controversial among some circles, isn't there? There's some that believe it's a bit older, some that believe it's a bit younger.
Yeah, I mean, I think a bit older and a bit younger. What type of range are we talking?
We're talking. I guess the extremes are like 4.5, maybe a tiny bit over 4.5, maybe 4.51 billion years old on the old end, and then the young end potentially down to like 4.4 billion years.
Okay,
but
so quite.
It's. I mean, it's 100 million years, but I think I don't know how many people seriously believe 4.4 billion years. It's a bit hard to tell because a lot of the papers will kind of conveniently sidestep saying like this is definitely the age of the moon. The problem that we have is essentially to do. I mean, it's the old sample bias chestnut associated with the Apollo samples, right? We know that the near side of the moon that the Apollo missions visited is very, very biased. It's right. I mean, all of the missions are either in or quite near to this, what we refer to as the prosolarum creep terrain, which is incredibly enriched in a lot of sort of rare earth elements and radiogenic material compared to sort of the highland regions of the moon. So we have this problem that that in itself means that our isotope systems are potentially a little bit kind of messed up in a way, or certainly very biased. And certainly we see this with the lead isotope data. We get this model age for some kind of differentiation event happening at about 4.37 is what our sort of lead data suggest. Now this age pops up in samarium neodymium and rubidium strontium and lutetium hafnium models. And it's really hard to say what this model age means, this 4.37. But what we do know, certainly, I mean, speaking from the point of view of lead isotopes, is that you are almost certainly getting this overwhelming signature of the sort of what we call the creep formation, or the formation of the sort of creep reservoir. So this is this sort of geochemical signature of these very enriched in these incompatible trace elements. And so, that signature sort of acts as a bit of a brick wall, and it makes it very hard to see what's happening earlier than 4.37. And to a certain extent, that's part of the logic for some of the sort of young moon theories, is that if you say 4.37 is when the sort of the creep formation, the creep reservoir formed at the end of the magma ocean, then we have models for how long magma ocean crystallization should take, and it shouldn't take a very long time. So the formation of the moon wouldn't have happened much before sort of 4.4 billion years. but there are all sorts of caveats you can start playing with, like can you make that crystallization more protracted by sort of tidal interactions with the Earth, or just really intense impact bombardment, or all manner of different mechanisms. I think as far as I'm concerned, the biggest problem is the sample bias. I think it would be really interesting to start, when we start getting samples from further away from the creep terrain, seeing if we see this same 4.37 signature.
So in terms of sample bias then, to what extent can lunar meteorites help then if they're sampling areas outside of...
That's a really
terrain?
interesting question. And there you come up against the thorny issue of like sort of terrestrial contamination, especially with the lead system. So there are some,
because lead's quite mobile, isn't it?
Yeah, and I think one of the problems, well, not I think, I know, I could be more certain than this. One of the problems that we suffer from with lunar samples is we know that there is a much higher ratio of uranium to lead in the moon as a whole. This has generally been attributed to the fact that lead is more volatile, and potentially you lose a lot of lead early on in, like, probably in the formation of the moon. What this means, so it's kind of a blessing in one sense, because it means that if we measure true sort of initial lead compositions in our lunar samples, that it looks drastically different to lead compositions that we see in sort of rocks from the Earth. However, it kind of goes both ways. It also means there's very little of that lead in the first place to measure on the moon. And if you even get a whiff of sort of terrestrial contamination, it just completely drowns out the signal from anything else. So we've seen this. I collaborated with Roman Tartez and with Mahesh Anand, and we analyzed, there's sort of relatively well-known meteorite, this it's Kalahari 009, which is sort of thought to have the oldest basaltic material that we know of from the moon. And I mean, you can see really clearly when you start like putting sim spots down in the veins of sort of terrestrial sort of altered material, you can see just how easily contaminated the sort of lunar lead compositions are by the terrestrial lead. So it's a real problem. That said, there are some sort of tantalizing little hints of maybe some differences in the lunar meteorite collection. A lot of the guys in Japan who have measured lead isotopes in lunar meteorites, and they've been doing some stuff even early as the 90s was some of the first measurements they got on some of these meteorites. They were suggesting sort of potentially terrestrial like lead isotope compositions in some lunar reservoirs. I'm always really careful when I talk about that work, not because I don't think they're good at what they do. I think that they're great, and the work that they have done is really, really impressive. I just think that at the time that was being published, we perhaps didn't realize quite how weird lead isotope systematics were in some lunar materials. And I'm still just a bit suspicious that some of those potentially sort of low uranium lead ratio sources that were identified in these papers, I suspect that could just be the effects of terrestrial contamination. But we should check it out for sure. It's like up there with I don't know, with getting new samples directly from the moon itself in terms of importance, I think. And we, at least with the meteorites, we can do that now. So one of my colleagues in Stockholm is already sort of looking into this a little bit. It's tough though, because you're still relying on having the right phases present in the samples.
And I guess if you want to look at more plagioclase rich highland material, then there's no lead in there inherently in the first place.
Well, yeah, but I mean, as you know yourself, John, because you very neat little segue into your own collaboration with us. Yeah, so what John is, I think, alluding to there is the fact that he's sort of detected some lead in Highland, it's sort of anorthositic
Yeah, not much
lithologies.
though. I guess to put it into context, though,
Not
I think the
much.
sample we're talking about, I think from memory, it's like 5 parts per million, which
Yeah,
is still a tremendously low amount when you compare it to minerals like zircon.
I would still be hopeful we might be able to get something out of this. So we'll see. That's very much like that's one of the other big goals. So I said that in terms of sort of importance or things that I think are interesting to find out. Some of these weird meteorites that the Japanese researchers were looking at are definitely up there.
Mm-hmm.
But I also think, trying to unambiguously measure the lead isotope composition of a north-acidic material is that would be like a super cool sort of slam dunk result if you could get it.
Yeah. So in an ideal world, if sort of sample mass was no hindrance, would you want to basically try and do, you'd want big sample masses and do sort of bulk rock stuff and pick out lots of the mafic minerals so you've got enough that you can actually measure with?
You know what, like it's a strange thing now that the technology has progressed, the analytical technology has progressed to a point where having a big sample mass in itself is not the most important thing. The fact is, and this is what potentially is going to slow us down with looking at like the anorthosites, is the fact that we're still reliant on having certain accessory phases. And so you can have as much mass as you want, but if your rock is just entirely anorthite, then you're going to struggle to analyze much else. I mean, we'll see. In theory, sort of anorthositic plagioclase should act quite nicely as a sort of lead sponge relative to uranium. Again, going back to this whole conversation of partitioning behavior, but it's again this problem of just the general low levels of lead in lunar material. It makes it very tricky.
Can I just ask you, so what is the importance and the implications of finding lead in these anorthosites then?
So what that potentially does is, this goes back to our issue of sample bias and the fact that at the moment, I think it's fair to say, even with like the Mare basalts, there's probably some degree of influence of the sort of creep signature in there to some extent. What we would really like to have is be able to start teasing apart all these kind of different reservoirs that formed in the lunar magma ocean. And one of the most important ones in that sort of whole thing is the Highland material, the anorthositic material. So if we could kind of nail the isotopic composition of those together with their composition, together with their age, then you can start plugging that into the model.
Yeah.
So at the moment, the model that we sort of published in EPSL like 4 or 5 years ago, that was really simplistic, and essentially it's just a 2-stage model where you have a kind of homogeneous bulk silicate moon evolving its sort of lead isotope compositions until you get to this 4.37 time. Then you have a differentiation point and everything else spills out from that one point. All of these different basaltic reservoirs form from that one point. That's hideously unrealistic. I mean, that's not going to be the way it works. Essentially that 4.37 point is almost certainly like a kind of averaging out of lots of different events in the magma ocean. But because of how weird creep is, that's the one signature that we see. That's the kind of overwhelming signature that kind of pulls everything towards this 4.37 age. But what you would really like to be able to do is isolate these other events. So isolate the kind of separation of mafic cumulates that form the Mare basalts, the anorthositic sort of cumulates that form the flotation crust. You want to be able to isolate all of those and then form a much more complicated model where you have multiple stages of magma ocean crystallization. So that's kind of what we were trying to do with the experimental stuff, because we realized with the samples that we have now, we've very much hit this brick wall and we can't get any further. So the idea was to sort of work it from the other direction and just try and build the moon ourselves. Don't worry, have your sample data on one end as like a goal that you want to reach. Say, okay, I want to reach these lead isotope compositions or these strontium isotope compositions at the end of the story. But start off just saying, well, can we do it ourselves with our knowledge of how things partition and with what we think should be crystallizing in the magma ocean.
Have you found it quite frustrating then with some of these challenges in terms of sample collection and stuff, driving at the specific question that you want to answer?
Yeah, I guess it is a bit frustrating. I mean, I guess the obvious example in that respect would be with regard to the new the proposed sort of Chinese mission, the Chang'e 5. So I am as excited as anyone is about getting new lunar rocks. I think it will be brilliant. And the fact that if they continue to plan to land where they were originally talking about in terms of some of the youngest basalts on the moon, that will be fascinating to see. I mean, people like Harry Hiesinger, who did all the kind of crater counting and all the sort of dating of basalt flows based on crater densities, they must be so excited about seeing the results of and seeing how old some of these potentially young basalts are. From my point of view, it's debatable how much those samples are going to tell us with regard to these kind of questions about early evolution of the moon, because you're still very much within that kind of creep terrain area that the Apollo missions visited. What I'm far more excited about is the prospect, sort of in the future, hopefully, of getting far side samples and the sort of much sought after SPA sort of mantle cumulate type samples. That would be fantastic. Sort of mantle xenoliths from the moon would be gold dust. But you know, we're gonna have to wait a while for that, I think.
You mentioned a bit about doing SIMS work, but then I think, did you also mention that you're using laser ablation on your experimental samples?
So all the experimental stuff I've been doing with laser ablation, I guess, primarily just for the reason that it's the method that has typically been used by the group here in Amsterdam, and I didn't want to be like the new guy in town telling them how to do their stuff. It has occurred to me on several occasions, though, when we're struggling for spot size and some of these smaller accessory phases, that going to SIMS could be helpful. You run into different problems. You then start requiring a need for sort of matrix matched standards, whereas laser ablation, you're much freer to just kind of shoot whatever you want and get absolute concentrations of things. So yeah, there are complications, but it's certainly an option to try and combine sort of SIMS work into that as well. But for the time being, the laser has been working very well, so I'm kind of not so inclined to use SIMS for this particular work. It's like different tools for different jobs. You know, like I know some members of the sort of SIMS and laser communities will be at each other's throats sometimes, but yeah, I guess they have their own pros and cons.
Is there a particular analytical technique that you really enjoy using over others out of the various bits of kit you've used?
I don't know that. Again, just so see, I always just like imaging stuff. I love electron microscope and microprobe work just because of the really childish enjoyment of like polishing up a sample and then putting it in and seeing it for the first time. Like I remember during my PhD, so my whole PhD project was about trying to identify unusual lithologies in Apollo 12 soil. What that meant in practice was that I had little grains, little sort of chips of basalt that were found in the Apollo 12 soil samples that no one had looked at before. And so there's something incredibly exciting about having like a section that, I mean, I made the sections myself and I polished them myself, and I knew that I was the first person looking at those tiny little bits of the moon. And so, yeah, I've always really liked just imaging stuff on electron microscopes, and it's also just appeals to like a geeky computer side of me that I just like playing around with images on my computer and like mapping out like element concentrations and making like pretty false color element maps and stuff. So that sort of stuff appeals to me. But then the flip side is you start playing with lasers, you're firing lasers at moon rocks. So it sounds better as like when you're describing what you do for a living.
Yeah, that's true.
Yeah, it's not actually very Buck Rogers in reality, but you can kind of keep the illusion up for a while. Yeah. Yeah, I don't know. But then I spent so long on The Sims in Stockholm as well. That also has its perks. Yeah, I love them all. Yeah. And like I say, they're all good for different things.
Yeah.
The one thing that I'm woefully inexperienced with is all the kind of sort of solution chemistry that people do. And to me, that I feel a bit guilty when I show sort of plots of our Sims data in front of crowds of people who do sort of Tim's work, for example. Mm-hmm. Because I know that those guys slave over every single data point, whereas we just set up like a run of 50 data points to go overnight and just have all that data. It's like, there you go. Nice. There's our like 20-point isochron. What's that? 4 points? Come on. Yeah, I feel I feel very guilty because it's, I mean, the precision that those guys get is still drastically sort of superior to what we can get on the Sims. So it's just, again, it's just different tools for different jobs.
Yeah.
Yeah.
Cool. Well, we've got one last question actually for you.
Okay.
And this is a question that we ask all our guests at the end of each episode. So if you didn't pursue a career in academia, what do you think you might have gone down in terms of a career route?
That is really difficult. I don't know. There's a part of me that would like to think I could maybe do some sort of science policy and advocacy sort of work. Especially like I mentioned earlier when we were chatting about the fact that my girlfriend's doing a PhD here in Amsterdam. She does all sorts of stuff on kind of climate change science. Mm-hmm. I feel sometimes a bit like I don't know, I worry that I'm not making much of a good sort of difference in the world as I could be just by analysing moon rocks. But I guess someone's got to do it, right? You can't really weigh up the importance of things in that way. But yeah, I think sometimes sometimes about sort of advocacy or sort of science policy advice. Mm-hmm. I don't know. It's probably hideously boring in the day-to-day.
Important job though. I think it's important to get.
Yeah, I mean, I remember talking to Mahesh Anand once about this, and I think he did a bit of this kind of work, like acting as a science advisor for a local politician. And I think his opinion of this was very much like, if you want to make a difference, that's the way you do it. Mm-hmm. It's the advisors to these people who are
making the decisions.
Yeah.
Well, that's cool.
Yeah, good answer. Yeah.
Mm-hmm. Yeah. Well, Josh, thank you very much for joining us.
Yeah, no,
it's been a real pleasure. And I hope I hope all the lab stuff goes well over the next few months.
I think so. I think we're kind of coming to a close now. I've just shipped off a bunch of samples to Munster, so I'm going to be doing kind of remote analyses by TeamViewer next week, I think. So.
Cool. Yeah. Not quite as exciting as going to Germany, I suppose.
Yeah, definitely not quite as good, but it's that's the times we live in.
Yeah. Cool. Anyway, Josh, thank you very much. And
thank you. It's really good.
Pleasure. To all our audience, we hope you enjoyed this, and we'll see you all again very soon. If you want some more Earth and Solar System content, do check us out on all the social medias everywhere, from the Twitters to the Facebooks to the Instagram. We're at Solar System on most places. All the information will be in the episode description. But until next week, we'll see you all very soon.